Crazy that the limit of that sequence goes to zero, yet its sum is infinite. Isn't that crazy? Yeah. Crazy stuff happens when you go to infinity. So once more, let's read this divergence test. If a sum, that means adding them up, converges. So if the sum is gonna converge, then the sequence, the individual terms must approach zero. That should be intuitive. Equivalently, if the sequence, the individual terms do not approach zero, then the series diverges. Okay? If the limit of the sequence equals zero, the divergence test is inconclusive. If this part, where my mouse is pointing, if this part is true, that does not mean this has to converge. We just saw an example where this part is true and this part diverges. Okay? So if this part equals zero, the divergence test is inconclusive. You don't know anything about that series. You have to go on to something, you have to work with it in a different way. But if the limit is not zero, then you know it diverges. That's why we call it the divergence test. It only tests for divergence. It does not test for convergence. Got that? A lot of people make that mistake and they misuse this test. So if that limit is not zero, then the series diverges. If it is zero, this test is inconclusive. You have to work it a different way. Okay, so this is what we just did with that harmonic. Here's what we just did over here. So here's this statement. The harmonic series diverges even though the terms of the series approach zero. So the reason, any people here play an instrument or sing or something? Anybody into music? Yeah? Yeah? Okay. So, anybody play guitar? Yeah? So when you cut the length of the string in half, you get the octave, correct? Same note, an octave up. When you cut that one in half, again, I think you get a fifth. I'm not sure. So if you imagine a guitar string or any kind of a piano string, any string, if you cut them by these ratios, cut them in half, cut it into a third, the length, into a fourth, into a fifth, those create harmonies. And that is why it's called the harmonic series. If you've ever held the sustain pedal down on a piano and then yell real loud and then wait and listen, your yelling will cause the strings to vibrate and you'll hear some harmonies coming through. Those harmonies are related to these ratios. Okay. The Pythagoreans get credit for this. The Pythagorean theorem, those people get credit for this. So that's why it's called the harmonic series. It is related to music. All right. What we just did motivates another test. It motivates the integral test. And hopefully this will make sense to you now that you've seen this. It says here, suppose f is continuous, positive, decreasing function. So those three things must be true. It has to be continuous. I mean, if you draw a graph, you can draw it without lifting your pen. There's no breaks, no asymptotes, nothing like that. No vertical asymptotes. So it must be continuous, positive. It must be above the x-axis. Decreasing from left to right, it always has to be going down. It can never go back up. For x greater than or equal to 1, and let a sub k equal f of k. So we're just creating a real valued function for the a. Oops. All our series and the integral going to infinity. Either both converge or both diverge. In the case of convergence, the value of the integral is not equal to the value of the series. So the areas of these rectangles and the area under this curve either both converge or they both diverge. So what does that mean? That means when we have a function that we don't know how to work with, divergence test doesn't work. It's not geometric, which we already studied. It's not telescopic. Another option then is to write it in terms of x and take its integral to infinity. If that integral converges, so does the series. If that integral diverges, so does the series. Is that what you're asking about?
Yeah.
So that's our next test, and I didn't bring the sheets, but it's the 1, 2, third one down on the front of your sheet here.
Did the integral test prove it to be contrapositive?
Contrapositive is always true, so what we're saying here is if the integral converges, then the series converges. So the contrapositive would be if the series does not converge, then the integral does not converge. And that would be true. And you could say it the other way. If the integral diverges, then the series diverges. But you could also say if the series does not diverge, then the integral does not diverge. Yeah. Contrapositive is always true. Let's do some examples that use the integral test. And these examples are going to lead us to another test called the P-series test. So be watching for a pattern in these examples. Get to the right page. Get to the right chapter. There we go. All right. So we only had like 10 minutes left on Wednesday to do all this, and that's what I did not want to rush through. And I'm glad we didn't. K equals 1 to infinity of k over k squared plus 1. Yes.
Sorry, excuse me, but you know, you said that if the integral is the same, meaning it converges, then the sum also converges. But let's just say we get a certain value for converging for the integral. Is it the same value as the sum, or
No.
is it different? Okay.
And we'll talk about that. It was in that statement on this slide, but yeah. No, it's not the same. And I'll talk about that when we do this. All right, so we look at this, and we might first want to say, okay, well, let's check it with a divergence test. So to do the divergence test, we do the limit of the sequence. So we do the limit as k goes to infinity of just that expression. This is not the limit of the sum. It's the limit of the individual terms in the sum. And we know from first semester calculus that if we have a polynomial over a polynomial, the degree of the numerator is less than the degree of the denominator, that the limit goes to 0. When that happens, the divergence test is inconclusive. If that had gone to something other than zero, if that had gone to a number different than zero, we would have said this diverges. But because it goes to zero, the divergence test is inconclusive, we don't know anything, all right? This is not a geometric sequence or series. If it was a geometric series, we could use the geometric methods that we learned to analyze it. It is not a telescopic series. So none of those work. Geometric doesn't work, telescopic does not work, divergence test does not work. Let's use the integral test. To do the integral test, we're going to do the integral from 1 to infinity of x over x squared plus 1 dx. This equals the limit as b goes to infinity of 1 to b x over x squared plus 1 dx. So now we have to apply our section 8.9 methods for improper integrals. This will require a u substitution. So du is 2x dx, so we need a 2 here, and we need to counter it with a 1/2 out there. So this equals the limit as b goes to infinity. No, sorry. Come back to that. This equals the limit of 1/2. This will be 1 over u du. Now, if we want to put bounds on it, we have to write them in terms of u. So our lower bound was 1. If we put that into x here, 1 squared plus 1 is 2. And our upper bound is b. If you put that in for x there, you get b squared plus 1. Usually I just leave the bounds off, but there you go. Now we can put b to infinity. All right, antiderivative of 1 over u is? Natural log u, is that what you said? So this equals the limit as b goes to infinity of ln absolute value u. And our bound, since we're in terms of u, we're from 2 to b squared plus 1. So again, usually I would write it back in terms of x. So u is x squared plus 1. That will always be positive, so absolute value is not required. Then we can put our original bounds, 1 to b back on, like that. Put b in. We get ln b squared plus 1 minus ln of 1.
Why is it from 1 to b? Is it,
Because I changed it from u back to x.
so did we use the original?
Yeah, so when we're in x, it's 1 and b. When it's in u, it's 2 and b squared plus 1.
Okay.
Because I used this here to convert these to for u, but I went back to x.
Okay.
So I was just saying, I'll talk about this after we finish here. ln of, we're taking b to, this is supposed to be infinity, not 0. b goes to infinity, ln goes to infinity, and ln of 1 is 0, so this equals infinity. Which means this diverges by the integral test. And I want you to actually write that when you do these problems. Diverges by the, and then state the test that was used. So, the integrals test says that if the definite integral of this expression from 1 to infinity diverges, then so does the sum. If that converged to a finite number, then the sum would also converge. But that does not mean the sum equals that number we get from the integral. They're not the same.
What happened to the 1/2? That's outside of the,
Oh, it's still there. 1/2. Thank you. 1/2. There's a 1/2 in there. But 1/2 of infinity is still infinity. 1/2 of 0 is still 0. But thank you, it technically should be.
Helps for the notes.
All right, there's the integral test, an example of it. Now, let's do this one. I want to keep them all on the board so we can look at them. 1 over k squared plus 4. So we got the sum. K goes from 1 to infinity of 1 over k squared plus 4.